So my name is Zeeshan, Naseh. I'm part of Cisco Advanced Services data center networking team. What we do is we work with service providers and enterprise accounts and design and build data centers for them. Part of that is building disaster recovery solutions for the clients. Today what we're going to talk about is disaster recovery and geographic server load balancing. The session is focused on front-end access to the application. What are the front-end technologies that we can use to access our data center based on availability, based on geographic proximity, and such. To start with, we'll talk about what distributed data centers are, what are some of the topologies to go over, what warm standby, what hot standby means. A lot of you might be familiar with it, but it's just to set the stage and everybody's on the same page. Then we'll go into the technologies which are available to us, like DNS, how we can use that to content routing and go to a particular site. We'll also talk about using IP. There's the technologies available now on the content switching side, where we can inject routes into the routing domain, which can be carried over for intranet-based application to the OSPF, or for external application to BGP. So the clients can come in using IP anycast to the proximate sites. We'll also go over HTTP redirection, how that works and what's all that is about. And at the end, I have some case studies that we can go over. During this session, if you have any questions, just go ahead and ask, and I'll address it. I'll be around after the session also, so if you want to go deeper into any subject, we can do that. So distributed data centers. The key idea behind distributed data center is to avoid a single point of failure, to make sure that all the key applications which are being hosted in the environment, for example, it might be belonging to if you're an ASP service provider, it might be belonging to your customers or clients, and you may have services available for additional revenue to have their application, their servers distributed across different geographically dispersed locations. Scalability, right? You want to scale. A lot of times, if you are scaling an environment, you scale within the data center, but there are ways to scale, across the data center, which makes sense when you're doing distributed data centers. Disaster recovery, ISP, redundancy, we have all these requirements in there. Better response time, that's one of the keys nowadays, since a lot of the applications out there are web-based. So you want, and all your client base is global. So you want to make sure that the content or the application the client is trying to access, may that be from your internal organization or external user base, they go to a site which is closest to them. So optimal content routing. Business continuity is one of the key drivers here. Just to cover some of the terminology that you'll hear around distributed data centers is business resiliency. Business resiliency basically means how resilient your environment is when a failure happens. This includes the infrastructure, how redundant you have set it up, what kind of redundancy you have within the environment, the content switching, the servers themselves, the application themselves, how resilient is the application when a failure happens. There are a lot of applications, if you just flap the link, right, if you bring the links up and down, the whole application crashes. So it needs to be resilient in terms of if any failure happens, it should be able to recover dynamically instead of doing a server reboot. Business continuance is the business should continue. If you're a mobile service provider, if people are coming into your websites buying cellular services, they should continue doing that. Doesn't matter if your primary data center goes down for any reason. Disaster recovery is mitigating the impact of a disaster to recover and continue to service the customers as they're coming in. The time between failure and recovery is it depends on the technology that we are using, right? If we are dependent on a DNS push, then it can take up to 24 hours. The key drivers, here again, putting mission critical application within the data center, the ability to access the applications when a failure happens. Teleworking, you have your own engineers and staff coming in using VPN and such. So you can able to access the environment. Now, when the disaster happens, right, what exactly is the disaster recovery is to mechanism to react when a failure happens. The failure itself, if you look at it, it could be anything. Within the data center, it could be an infrastructure failure. It could be that all the servers associated with an application went down. It could be a content switching device failure. It could be a failure on your link up to the ISP that went down. So all these, whether there was a tornado, power outage, so all that amounts to failures within the data center. Now, it depends, when you do disaster recovery, it relies on data replication. Because within the data center, the key resident or the key host within the data center is data itself, right? On top of that, we have a lot of layers, but data itself needs to be replicated. How you're replicating that data, that's relevant also. Sync, async, it would depend how long of a time period of data are you going to lose if you do async, let's say. If you do sync, then pretty much you're not going to lose any data. Typically, this is referred to as warm standby. It means that you have an active site, which is servicing requests, and you have a standby site, which has the applications that the user can access, but in a steady state, there won't be any users going to the backup data center. I have some topologies which can explain this better. So these are very simple topology showing a data center where you have a content switching or server load balancing or application load balancing device, which is receiving the request and sending it across multiple servers. So it works fine, then the business requirements comes in, or if you're an ASP, you start to, you decided to, okay, we're going to start a new service where we're going to offer this disaster recovery for our clients. And we're going to have their servers in a different location present also. So just in case you have a disaster in your primary data center, they can still get their application. So you have a primary data center, you establish a second DR site. The DR site here, it may not have all the high availability which exists in the primary data center, right? Your primary data center is going to have dual routers, dual home servers, and everything. In your DR site, since it's only being used in warm standby mode, you may not have all the layers of redundancy, just to save cost. So still, you have a DR site, but you're still serving all your data using your primary data center. Geographic server load balancing, also known as global site load balancing, global server load balancing, means the same thing. It means you have multiple data centers, active, and you're distributing the request using a content routing mechanism across the sites. So the idea is that you're hosting the applications in both the sites. All the components of the applications, the web front end, the middle tier, the database, and data itself. So they're independent of each other, and as users go to both the sites, you replicate, you service the users, and between the sites, you replicate the data to each other to make sure they're both in sync. This is often associated with DNS-based deployment. The DNS is a control plane which we pick to achieve this. But that's not the only mechanism, and today we'll talk about some other mechanisms also, like using IP Anycast, or using HTTP redirection. Again, a simple topology, and we move towards a GSLB environment. We already had the DR site up. Now what we are doing is that we are servicing requests from both the sites. Now, end-to-end application flows need to work in both the sites, so you need to have all the tiers of the application to make this happen. How you select the sites from data center 1 or data center 2, that's where the content routing piece comes in to make that happen. Any questions so far? Okay. We'll go over a few topologies just to understand the distributed data center architectures, and then we'll go into the technologies that we can use to make this happen. So within the data centers, we typically have 3 tiers. We have the web front end, we have the application tier, and then we have the database tier. So if you are in ASP, you would have different silos which is servicing all of these tiers for your customers. There would be questions of if you want security between the tiers or not. There might be firewalls between the tiers, but overall, that's what you would have. So initially, the user will go to the web tier. From there, the server will initiate sessions to the middleware. From there, you will go to database and get the requested content. When we have distributed data centers like this, in the middle, we might have optical, Metro Ethernet, or in this case, it's showing is fiber channel over IP that's being used to replicate data between the data centers. So the first layer, which is at the top, is showing content routing. So that's where the site selection happens. That's where our key technologies are, which are DNS, IP routing, linked with RHI, some kind of route health injection protocols to make that happen, and HTTP redirection. So these are the technologies that we'll focus on today. So if you look at it, right, I mean, when a user goes to any application, to start off, what we are doing is we go to a browser, we enter the domain name on the browser. So behind that, we have a stub DNS resolver which goes in and try to resolve that domain to an IP address. So when that request goes out, it goes out to the internet, to the intermediate, to all the DNS servers. At the end, it will come to us, to our authoritative DNS server. So we have some control there. So we can give a specific IP address to the user so they go to a specific site. So that's one. And then after that happens, the user issues TCP connection to that IP address. So that enters the IP control plane. So we can use IP over there to send the user to a particular site. After that happens, the user enters the data center, and we terminate the session on some kind of load balancer. The load balancer has the control there to send HTTP redirection to the user to go to a particular site. If it is an SSL-based application, we can offload SSL, look into the clear text HTTP header, and make a decision. So these are the 3 control planes that we'll address. Content switching is another layer within the data center. So this is where we are load balancing the applications themselves, right? To provide high availability for the servers, we are getting the user requests. We are distributing that user request across a set of servers. And that load balancing is happening based on whatever the configured parameter is. It could be least connections, round robin, any of those mechanisms are available. Plus, it's doing health monitoring, right? It's checking the health of the application itself. So before I hand a request to a server, I make sure that server is healthy. And not just the server, but the application daemon running on that server is functioning properly. So we have extensive keep alive capabilities that can be utilized here. At the back end, we have storage, which is connected over optical and whatnot between the data centers. The idea here is that we are replicating data between the sites. The mechanism could be sync or async between the data centers. This mechanism that we have to keep in account when we are thinking about these things is that how geographically dispersed we want the data centers, right? Because if you do sync, then sync basically means that we're going to go to the other site, write the data, then write locally. So there's latency involved. With async, there's a duration. Okay, I'm going to do a replication every night or so. So there might be a 24-hour, 12-hour gap. If you have a failure, you're going to use that much data. So the architecture should account for the following, right? Accomplish the failover of traffic, without any oversubscription. So if you're getting a certain amount of traffic on your primary data center, and when it fails over to the backup should be able to handle that much traffic that goes in on the plumbing itself, on the layer 2, layer 3, your content switching or load balancing environments, your servers themselves, right? You should have the same amount of capacity on your backup side. So if you look at it, basically, just two terminology, you'll hear warm standby, hot standby. Warm standby basically means that it's a DR site. We have a active data center, and we have a standby data center. So active data center is the one which is servicing all the requests which are coming in, and the standby data center exists just in case if there's a failure in the primary data center, we'll service requests on the standby data center. Hot standby is active-active, so both the data centers are servicing requests. It could be that we are servicing the same application from both the sites, or we are servicing different application from both the sites, right? So you have application 1 active on data center 1, application 2 active on data center 2, but you're utilizing both the data centers' resources. So you have a primary data center, the secondary data center, request goes into the primary data center. If there's a failure, at that point we'll switch and start sending requests to the secondary data center. Now this implies that if the secondary data center is idle, then a lot of the phase 1 deployments, basically, as I indicated earlier, it won't have all the redundant components within it. Plus, we have to ensure by having some change windows or weekends and whatnot to make sure that the secondary data center is ready to service requests if a failure happens. The switchover between the sites could be manual by doing a DNS push, or it could be dynamic using the technologies available. The advantage here is that it's a simple design. It's a typical phase 1 deployment where you create a DR site for some of your critical applications and have it present in the DR site. It's easy to build and maintain, easy to build because you have already built your primary data center, you know how it works, how all the interconnects, how the infrastructure is. You're replicating that in your DR site. It's easy to maintain, meaning all the flows are symmetric. You know where users are going to. All the users at all times go to the primary data center. They don't go into the secondary data center. Simple configuration, underutilization of resources. So over here, a lot of times, what can be done is that in your DR site, you can still host some applications in your DR site, some internal applications in the DR site, and have the primary user-based applications in your primary data center. So what that does is that when you have your internal users going to the DR site, you are checking the availability, dynamically checking the availability of the DR site. You don't have to have change windows to do that. So dynamically it's taken care of. There could be a delay in failover if you have manual switchover. Hot standby, both our data centers are active. So in this example, we have application A and application B hosted on the primary data center and application C hosted on the secondary data center. We can set this up so that all the applications are hosted on both the data centers, or some as in this case, some applications are hosted in the primary data center, some applications are hosted in the secondary data center, and we have the backup for each application on the other side. So if your primary data center goes down, you have the secondary data center, and it's going to start servicing all the applications. Key advantage here is the good use of resources due to load sharing, ease of management, in a sense that both the data centers are active. I don't have to have separate change windows to check the availability of the data center. It's a little complex. It's a typical phase 2 deployment. Complex meaning if I'm hosting both the application or both the sites, I need to have all the elements present in both the sites. Plus, in terms of data replication, I have to replicate data from both the sites to each other instead of doing from the primary site to the secondary site. Data mirroring is happening using sync, async between the data centers. Now, having covered that, we'll start going over the technologies that we have that we can use to do site selection. The first technology that comes to mind the key control point that we discuss is DNS. So that's the DNS resolution, which the request through the DNS control plane always comes to us, to our authoritative DNS server. So we can put smarts in our authoritative DNS server and make decision on where the client needs to go. So we'll discuss that, and then we have route health injection. Route health injection is basically your servers are being load balanced by content switching devices, right? Your SLB devices. So what we can do is that we can use the smarts available on those SLB devices and inject routes up to your routing domain for the virtual IP address. Now everything is being hosted by virtual IP addresses, right? So if anybody wants to go to any domain that doesn't map to a singular, it maps to a singular IP, but behind that we may have hundreds of servers, right? That's how you scale. So for those virtual IP addresses, we can inject those up to the routing plane based on the availability of the servers. So if my application is up, I'm going to inject the routes to the routing domain, otherwise I won't. Then the final control point is HTTP redirection. That's when the request actually makes it to the SLB device. The SLB device can look at the HTTP headers, and we can make these solutions based on cookies or just parameters within the HTTP header and redirect the user to a particular site. We can also take into account the user's IP address, the client IP address, and do redirection based on that. So particular sets of clients goes to a particular site. But that, of course, applies to our enterprise environment because you know the source IP address. If it is internet-based application, we don't know the source IP address of the client. Just quick overview of the DNS. To start off, we have a domain name that we are trying to go to using a browser or a custom application behind which we have a DNS resolver within the PC. So we enter the domain name, let's say on a browser, and we try to, and the browser gives it to the DNS resolver within Windows, who goes out and tries to fetch the answer for it. Now, the DNS query is a record query which comes out to the DNS server, and the DNS server responds with a record answer. When this response comes in, if you have multiple addresses tied to it, you will get those multiple addresses to your system, and then your system can decide based on how the configuration is that you can pick the first one or round robin across it or the second one. So this is pretty much what it is. Now, it's a key to understand how exactly this works. What are the two modes of DNS that we have, iterative and recursive, right? Iterative basically means that I'm going to go out and fetch the data from each site. So I'm going to go to the root server. Root server is going to hand me the intermediate. Intermediate is going to hand me the authoritative. So that's typically how it works from your enterprise DNS proxies to out to the DNS control plane. So our laptops go to our enterprise DNS proxy, and from there we go out, or service provider DNS proxy, and from there we go out and fetch the data. Recursive is basically I go and get the final answer. So this communication that you are seeing here, so this is basically your user system right here, laptop, sending the request to the DNS proxy. From there it's going to be iterative. It won't be recursive like this is going to be iterative, as we discussed earlier. A couple of RFCs that describe that. So the authoritative DNS server, which we showed earlier, which is handing off the final response, final answer, the mapping of the domain to an IP address. That's a device which we call DNS-based site selection device, which is available from a lot of different vendors. And the key idea behind this device is to make site selection decision based on configured load balancing or selection parameters and send the user to a particular site. This device is sitting at the top, content routing plane, and it is talking to your content switching or server load balancing nodes and making sure those sites, not just the sites, but the application residing on those sites is healthy. So it's exchanging heartbeats with those sites, probing to making sure those are available. Not just that, we can do least loaded based balancing method, where we actually check the load on each site, on each data center, and make decisions based on that. The key here is that you have a authoritative DNS server. So this is the smart DNS device, which is making the decisions for the virtual IP address. The virtual IP addresses are hosted on your load balancing elements within the data center, behind which we have the servers, right? So these smart DNS devices, they are exchanging keep alives with those SLB elements and making sure they are available to respond to user requests coming in. The client initially goes into the DNS proxy, may that be for the service provider or within the enterprise, which goes to the root. Now the root responds back with the authoritative for .com, the authoritative for Cisco here, and then to the authoritative DNS server, and we get the final response back. So from the point of view of this smart DNS device, what's the source IP address that I see? I see the source IP address of DNS proxy. So I know its source IP address. I don't know who the client is trying to reach the site. So if I'm going to do any kind of proximity-based solution, if I'm going to implement my design such that I have distributed data centers spread across East, West, and Central US, right, then it's going to be based on the proximity of the DNS servers, right? So the client, if the client is using VPN, the client could be sitting in LA and the DNS server could be in New York, but we're going to send them to a site in New York because that's where the DNS server is. Okay, and the other key here is the selection of the sites themselves. Like if you have multiple NS records which goes out to the name servers out there, right? Then the name servers, it's built into bind. The name server selects the closest authoritative server. Basically, the way it works is that if you have multiple NS entries, multiple IP addresses within the NS response that you get, right? So the name server is going to go out and try the first one, get the response, clock it, and check the TTL. Then it's going to go to the second one and clock it, and it's going to go down the list and check all of them and see who's going to respond the fastest. So dynamically, the name servers try to go to the closest available authoritative DNS server. This is the way we go to the closest root server. There's about 13, 14 root servers out there, so we dynamically select the closest root server to us. So this proximity is built into bind. So after we get the final response, we'll go to the data center from where we get the VIP virtual IP address, route to it, and get the content. Okay. So over here, what we are showing is that the users are coming from different medium, and they're entering the routing plane, and they will be routed to the global site selectors on 2 different data centers, where we have the content switching elements and we have the servers located. So as the request comes in, it follows the same route to .com to the authoritative, and we get a response back based on which site is the proximate to the client, and we service the data to the client. Just to look at it from the IP perspective, how we're configuring things, how the solution lays out, we have the primary DNS server with for the particular application, let's say www.foo.com. For that, we have NS entries, 2 NS entries. So we're saying authoritative for that is GSS1 and GSS2, and that's available in the NS right here. So these IP addresses are the interface IP addresses on these smart DNS devices. Each of these devices are maintaining keep alive with each of the load balancing devices, which in turn are maintaining keep alive to each of the servers which are available. So at the end, from this device perspective, when it checks the health from each of the SLB elements, we find the health of the servers sitting within the data center. So here, as the request comes in to a local DNS proxy, we make it going through the DNS control plane to the primary, and we get the NS record with 2 entries. So at this point, we're going to go to the first one, and we'll get a response back with the answer for that site. Any questions so far? So a couple of things to see here is that when we are maintaining these keep alives across the SLB nodes from the GSS, right? From this site, we can send these keep alives over the internal network between the data centers or externally through the internet also. So we have clients who do both. So when you send it through external internet, you ensure that the links into the data center is functional also. So you have another layer of redundancy. Of course, when you send these keep alives, these HTTP and such packets, you can put security within it. Some of the methods that we have available, just like we have methods available for server load balancing, we can load balance requests to servers based on load, based on least connections, based on weight, or we can even run some protocol. We have SASP, we have DFP protocols available that run from the content switching device to servers application to check the availability of the resources within the servers like CPU and memory. Similarly, we have a bunch of methods available in the smart DNS devices. This is pretty common across the vendors. We have ordered list. Ordered list basically tells you that I'm going to put multiple IP addresses or multiple VIPs for a particular domain, right? So domain and domains maps to answers. Well, I have multiple answers for a particular domain, but service the answer only in the order that has been specified there. So give out the answer for the first one. If the first answer goes down, then go to the second answer, and so on and so forth, right? So that's the advantage of ordered list. So it's a way to do active, passive, or warm standby, dynamic warm standby between the sites. So we are controlling that using DNS. Second is static proximity based on client's DNS server's IP address. So that's what indicated earlier, that what we see from these devices is the dproxy's IP address, not the client's IP address. So we can use ACLs and such and create static proximity for particular dproxies. right? This feature is available to provide dynamic proximity also, where these smart DNS devices, they send out these TCPs or ICMPs to the D proxies and check the round trip time. So by that, they calculate how far are these D proxies from each of the sites. And we create a database out of it. And as the request comes in, we send the request to the closest proximate site to the client. Client's D proxy. Round robin is available, weighted round robin is available. So if you have data centers with different load, different capacities, different server counts, then you can use weighted round robin. Least loaded is available also. Least loaded is basically where we run some custom protocols from the load balancer to the SLB device and check the load information from the SLB device. How busy are the servers? How busy is that entire site? We have source address hash, we have domain hash. So that is used to stick for site stickiness. When you have these users coming into a particular site, right? Depending if you're an ASP and what application you are, depending on the application that you're hosting, a lot of these applications use databases or information local to that site. Within that middle tier application within the site, there might be a SiteMinder or some entity sitting within the data center authenticating the users, but all the application is sitting within the servers. For example, a shopping cart per se, right? So we need to make sure that during the duration of the session, we don't hop the client to the other site, which is possible, right? Because we have these DNS refreshes, which are there in different browsers, i.e. Netscape. So they time out and they refresh the DNS. And if we get the request back to us, to our alternative DNS server, we do not want to send the same client to a different site. We want to stick them to the same site. The site stickiness becomes relevant there. And one of the approaches to do that is using a domain hash with a source IP hash. DNS race is available. Basically, idea in this technology is that you have multiple data centers and you have these smart devices. When you get a request to a central device, that device tells both the sides, okay, this IP address was asking about this specific domain, answer for this specific domain. Go ahead, send in the response. So both of them send the response, the race condition. Whoever reaches the client first wins. So that person is most likely going to be the closest to the client. Any questions? Okay. So the key advantage of using DNS is that it's easy to deploy, easy to manage. You can put a lot of control in this. For maintenance, if you want to put a site down, take a site out, you can easily do that using these smart DNS devices. Go there and take those answers out, so the users won't be going to the site which has been brought down for maintenance. So everybody will go to the other site. So those are available, easy to set up any kind of load balancing that you want to do, easy to stick the user to a particular site also. You have some limitations based on DNS caching, which is out there, right? You have DNS caching, which could be done at the service provider side. It could be done on the enterprise cache devices. It is done, as we know, is done on the browsers themselves, different timeouts for different browsers. So if you get basically what happens is that from your smart DNS device, when you're going to send an answer, you're going to have a TTL associated with it. You're going to say that this answer is going to be for 10 minutes, right? So all the devices out there which is going to be bind compliant, they're going to honor that and going to say, okay, that's fine. We'll just cache it for 10 minutes. But you may want to save bandwidth from your DNS proxy out to the internet. So you may cache it for longer. You already have that control in your DNS proxy, pretty much all of them. So you can cache it for longer. So you get a response, and let's say you cache it for an hour, and during that time, if that site goes down, then everybody sitting behind that service provider won't be able to access that domain. It's out. Similarly, for caching within the browsers, So caching within the browsers, as long as you have the browser up, there's a cache built in memory, which is going to be 15 minutes or 30 minutes. And during that time, what the problem that the browser caching mainly causes is the site stickiness issue. So the browser does a refresh, the request comes back to us, and we send the user to a different site, right? So we want to make sure that there is some kind of site stickiness available. Any questions? Okay. Now we're going to talk about how IP can be used for making this site selection. Route health injection is basically a feature which is available in most server load balancing or application load balancing devices. What it does is that when we have these virtual IP addresses hosted on the SLB node, and behind that we have all these farms of servers, we're checking the health of each of those servers, and if those servers are healthy, I'm going to inject a route from the SLB node to the routing domain. In Cisco's case, it goes from our load balancer to the MSFC, and from there we have control. We can do a lot of things with it. Since we get that route, we know that the VIP behind that route is a /32. VIP behind that route is active. So we can redistribute that into OSPF or BGP and bring users in using IP. So the idea here is that both the sites that we're going to have, in the case of DNS, we had different IP addresses associated with each site. In the case of IP-based solution, we're going to have the same IP address hosted on both the sites, right? And we're going to rely on, if you want to do active backup, right? If you want to do warm standby, then simply I'm changing the cost of the routes as it is going out. So everybody will go to the low cost data center from the routing perspective. So this is in the IP control plane, right? So this is how I'm achieving active backup. This costing which I'm doing is happening on the routing domain, the closest routing domain that I have, closest to the routing router, closest to the SLB device. So SLB device is going to inject a route, and right here I'm going to do appropriate costing as needed for each application. If it is an internal application, then we can let the /32 ride in the environment, and we can do different costing for different application, different /32s, which is fairly common to do. If it is internet-based application, then we would have to mask it going out to BGP, and still we announce it using IP anycast on both the sites. That's not as common a deployment, because to make that work, you have to work very closely with your ISP and make sure that both the routes are coming in. If you have multiple ISP, you need to ensure that it's still when the users will come in globally, they would end up at the closest site. But still, we have clients who have done that successfully. So if the low-cost route goes away, everybody goes to the other remaining route. So the way the RHI works is that from the load balancer, CSM is a load balancing module that we have. From the load balancer, I'm checking the health of the servers associated to a particular VIP. And if it is available, I'm going to send an out-of-band message to the MSFC, which is the routing daughter card on the supervisor, with that /32. On the MSFC, I have control that I can redistribute that route into OSPF and then carry it into BGP. Configuration-wise, this is just an example. On the CSM side, we have just a small keyword, advertise active, which tells the device that if the VIP is active, if the servers associated with the VIPs are active, go ahead and inject that route into the MSFC. If all the servers associated with a particular VIP are down, then I will not inject that route. I'll actually remove that route from the routing plane. So it provides, in a way, within your routing plane, you would only have routes going to active data centers, active sites. Here, I'm showing another example using a different load balancer, which has slightly different functionality, but it supports OSPF. So I'm using OSPF here to inject routes for the virtual IP addresses hosted on this load balancer to send across to the MSFC. So this communication is happening in band. This is OSPF running between the load balancer and the MSFC. I'm injecting routes using OSPF. Unlike the other one where I have a out-of-band control packet. Some configuration examples here showing a particular redundancy, box-to-box redundancy on the CSS. We have different flavors of load balance of redundancy within the dead device. So over here, we have we are taking the virtual IP addresses, which is 101, 102, and giving them metrics. And I see those routes appear with the next hop being .12, which is my interface IP address on VLAN 115, VLAN 115. So all these /32s appear on the MSFC in the routing control plane. So these routes will disappear if the servers associated with these VIPs go down. Right. A different redundancy model. This is using VRRP, which is pretty similar to using HSRP. And in this case, both the devices are active. Both my load balancers are active. So in this case, when I advertise these routes for the particular virtual IP address, so my virtual IP address is this right here. If you notice for 101, I'm seeing two routes going to .12 and .13, which is because there's an issue on the CSS. Why it does that? Because the WIF needs to be in the same subnet as the VLAN. For example, in this subnet right here, 10.115, exists in the same subnet as VLAN 115. So we don't have this duplication issue for 10.115, but we do have that for 10.116. So quick workaround for it, just we create a dummy VLAN, dummy SVI on the load balancer to make it think that, yeah, this IP address is part of a subnet, which actually belongs to a VIP, and it fixes the problem that we have. Again, we are monitoring the health of the servers and binding that with the availability of the virtual IP addresses. So the key advantage of RHI, it works with legacy applications which are IP-based. A lot of applications out there, they are still IP-based. They don't use DNS, so you go directly to a particular IP address. So for that, RHI works. It has a very good reconvergence time. We don't have any issues with caching and whatnot. It's protocol independent. I mean, the protocol could be anything underneath IP. It could be HTTP, HTTPS, UDP, custom TCP-based protocol. And it integrates very well, pretty much, with all load balancers out there, right? They have some kind of features available, or you can come up with some configuration. I gave a bunch of examples here just to show that you can come up with some configuration to make this work with pretty much all load balancers, right? They can inject the routes based on the availability of the servers. So the only active routes you have is for active servers. Limitations relies on /32, well, that's what's going to come in. It's fine if it is within my internal network. If it needs to go out, I can mask it. It requires tight integration between the application aware devices and the layer 3 routers. So you want to make sure that this routing that's happening to and from the application, they take a symmetric path, right? We have given this information to the routing plane. We have multiple routes there. Traffic can go here and there. But once it's coming into a particular site, we take the same path because we're going to go through firewalls and stateful devices. We want to make sure there's symmetry there. Pretty much all stateful devices, firewall, load balancers, they maintain state for TCP. internet deployment requires route summarization. Any questions on that? So the IP-based solution, I've actually tested that in the lab with BGP and simulating multiple ASs, and it works well, at least in the testing that I've done, and I have had a couple of customers who have deployed it also. Now, HTTP redirection, this is when the DNS resolution has happened. The packet has gone through the internet and has reached the data center, and it has landed on a particular SLB device or application load balancer. So I can look into the packet now. I can proxy the TCP, look into the HTTP headers, and make decisions on where the client should go, right? So these decisions are basically, I'm looking into it, and for example, I'm a load balancer sitting in Australia, and I get a request coming in for a particular domain, www.example.com, right? So I know, okay, this somehow I have landed in an Australian site due to some kind of proximity, and I'm going to the global domain. I need to go to a local domain within Australia, so I can redirect the user to come back in to the Australian site .au, and I will be set on that site. If the user request coming in is HTTPS based, meaning it's SSL based, then I have the capability to decrypt SSL and still look into the HTTP header and make decisions on that. The request which comes in at this point to the data center is coming in from the client, not the dproxy or any other entity. It's coming in from the client, and I can see the client source IP address. So I can make decisions on the client source IP address also. So after the DNS resolution, I would go to a particular site, and I may get redirected to another site based on the configuration that I have on that HTTP redirection entity. The redirection can happen on a content routing control plane. That's what it's shown up here. Or it could be done on the SLB control plane also. So this request can actually go to one of the sites, and this site can make a decision and send me to the other site if needed. There's ways available where you can send the user over the internal network on the other side using some source NAT on one device and send the user on the other side if needed, and service the content like that. HTTP 301, 302 basically is a location move message, right, which comes in, which tells the user, okay, the content has moved, go to this new location and get the content. So visibility to the client IP address, because client is the one who's initiating the TCP connect, so I can see it. I can distinguish between different hosts, different URLs, so I can look into the HTTP gets and look at what URL user wants to get. So I can redistribute requests based on that. So if somebody wants to go to application 1, I can say, okay, application 1 is primary on data center 1, so go to data center 1. Somebody wants to go to application 2, I say, okay, I can service it right here, right? Because we changed the domain, changed the URL on your browser will change also. And since the URL is different, you are binded to a particular site. And there is inherent persistence. So if you require stickiness to a site, you achieve it using this dynamically. It requires HTTP, so it's HTTP specific. If it is, as I said, if it is SSL, we can decrypt it and still do this for HTTP. Clients can bookmark a specific location, which may be bad, may be desired, right? Like the example I mentioned, that if you use a geographically different region altogether, which has different regional code for the domains, then we may we may want to change the URL altogether. Typically, if it is within the US, then it's not that great an idea, because what happens is that if they bookmark a site and that site is down, then you go nowhere. Any questions? Okay, we'll talk about a couple of real-world deployments. In this scenario, what we are looking for is fast disaster recovery between two remote data centers that we have. The application itself is non-DNS based, so the only control point we have left is IP to support these proprietary protocols. The sessions themselves for the protocols are very long-lived, so we need to take measures to ensure that we don't idle sessions out. Okay, so over here, two data centers, we have stateful active standby. We are injecting routes, RHI route into the routing domain, which is going into OSPF, and we are injecting these routes based on the health of the servers within each of the data centers. So we are doing health monitoring towards the server from the SLB nodes. When we have these routes going up, so if you, where is it? Okay, here. So if you have these routes going up, you have RHI coming in from the SLB node, CSM is the SLB device, to the router node, to the MSFC, and we inject these routes. We have two distinct routes coming out for the same domain, right? We send those routes out to the routing plane, control plane, internal network, and through the firewall out. So we have internal networks, so internal users can access these data centers based on these available IP addresses. BGP-wise, we map all the way BGP down, so take it across the firewall to the MSFC right here, and we inject the routes into BGP also. For BGP, we are injecting two different routes. So these are my internal networks, 10.19.12.13. For BGP, I'm injecting 10.13, 30, 13, and 14 with different metrics. So application 1 is hosted here, application 2 is hosted here. So the reason I have multiple IPs defined here is that my internal users can go to the internal IP address, which is just going to stay within OSPF, and my external users will go to the public IP address, whatever that might be, to each of the data center. And they will back up each other across the routing plane. So on the edge routers, I can change metrics if needed to adjust which routes goes where. So as I mentioned earlier, like in the DNS control plane, we have these smart DNS devices where we could go to a GUI and bring a site down for maintenance and bring a site up for whenever we need to, right? The maintenance becomes very easy. In this environment also, we don't have a central GUI, but we have control that we can go to these, we can change the routing also, redistribution and all that to adjust it. But better way is that go to the load balancer, and that the VIP which is being hosted, just turn it off. Just put it out of service. And that's all you would have to do to stop that route going out. So users will stop coming to that data center. Right? So it's not as simple as DNS, but it's doable by a single command line going to the SLB device on that particular data center. Any questions? So what we're doing here is route health injection. In the earlier, as we talked about, MSFC is running OSPF. We have MSFC is also running BGP, which pairs with the edge routers, and this BGP pairing is sent across the firewall. eBGP runs between the edge routers of the primary and secondary data center. We have firewall rules adjusted to allow BGP, OSPF in the core. So we have those VIPs for OSPF, which exist for internal users, and that works fine. Configuration example for this site right here. We have a key thing to note here is that the advertise is active. So that's my RHI. So that's how I'm injecting this route to the domain. And as you can see, I have multiple VIPs associated with the same server farm. App 1 is associated with multiple IP addresses because I'm going to use them for different purposes. I'm going to use one IP address for internal users to come in and another IP address for the external users to come in. And another thing to note is that one of the requirements for this case study for this customer was that the application itself takes a while to bring up. So, and the sessions are long-lived. So what we want to do is that increase the health monitoring timeout, the failed timeout, to a very high number. Over here is 18 hours. So you have it at a very high number to ensure that if a server goes down, you're going to keep it down, right? We're going to switch traffic to the other side and start processing requests on the other side. If the server comes up, we don't want to flip back, right? Because the sessions are long-lived. If they are established on the secondary side and they're working over there, we'll keep them there. We'll bring this side down by increasing the failed timeout. And when we need to bring this site up, we'll go there and do it manually. Okay, we'll have a change window and do it manually. So these tweaks are available, so you can address the specific application needs on how you want to handle failback if needed. So over here we have a varying capacity data center. So data center of different capacity, and we want to load balance a single application across them. It's a high volume application. Data centers with different server capacity, so we need to do some kind of weighted round robin here. Weighted, if you go with the IP route, it's very difficult to do weighted because you have both routes coming in. So either you can put metrics in there, so you prefer one over the other, right? So you have one primary site, but if you have both sides active, very difficult to do weighted. But with DNS, we can achieve that. So we have load balancers deployed along with GSS devices, and we are using these GSS devices to ensure that we have different weights for both the sites, and we get twice the number of users in one site over the other. So that's the key idea here. Any questions? Did you guys find this useful? I did. Okay. I mean, I know most of you are from service provider environments, but I get a lot of questions from service providers because they're going into this edge computing networks, where these edge computing networks needs to be deployed across the globe, and this questions of proximity content routing comes up again and again. And for ASPs, this is very valid, and for web hosting, of course. So these questions come up: how exactly can we do it? There's no perfect solution. The best way to do it is to use these technologies and come up with a custom solution based on the application that you have in your environment to make sure it works best. So in this one, we had appropriate ACLs for GSS. Within the smart DNS appliance that we have, right? A lot of the DNS types are not supported, so you can have name server forwarders configured to push requests to a name server, which is going to handle requests other than A record and NS records. We can do different weights for the, we can apply site stickiness using the source IP hash source IP hash of the DNS proxy. So site stickiness becomes critical in the environment where you're actually doing something with the user request, not just servicing content, but doing something with the user request. If there's some application which is keeping some database, so that becomes relevant. Static proximity is used for intranet clients because we see the client IP address. Client's dproxy is IP address. So even within the enterprise or service provider, you can have different dproxy in different regions. So looking at the source IP address of those regions, we can predict where the user is coming from. So there's some control available there. Quick configuration example is for your reference how we make this happen. This is basically least loaded. So this is where we are checking the load of the a particular site, application within a site from the GSS device. So we have some protocols that we can use to talk to the SLB device and retrieve the load information from it. So which are right here. We have app UDP, and this is how you add the DNS domain and make it work. Multiple V servers for different domains. So this is showing both the CSS model and the CSM model. Any questions? Yes. Right.
What recommendations do we have for situations like that, where you have different protocols that have to deal with administrative distance?
Right.
Clients, local clients, you want to have actually select the remote side, but because of the administrative distance, you're selecting the local instance.
Right. So I mean, the question is that how about we do with if you have different clients coming in, and client is coming in from the data center of buildings which are connected to data center 1, but we need to force them to data center 2 over the routing control plane. Then simply we can use, we can change the administrative distance on the routes and make the remote route better than the local route.
But the problem with that is whenever you change administrative distance, you actually terminate routing sessions. Like for example, BGP, you actually have to hard clear those sessions. And so you're going to have a service interruption there.
That's a good question. So what we can do is that bring BGP all the way down. So when we are distributing that into, but your question is when we are going from OSPF to BGP, right?
Well, like in your first case study, you had clients that are in the data center on the left.
Right.
Go back to that diagram. So you have clients in the data center 1 that you want to have reach bits that are actually data center 2 because of the way, these bits that you want to have active in data center 2 and some of them you want to have active in data center 1.
Right.
So if you're doing a sort of redistribution from BGP into OSPF, you're going to have protocol distance problems.
Right.
And so if you need to do maintenance or if you need to change the active versus the standby bit, you're going to introduce a service interruption. I was just wondering if there are recommendations or ways that you can do that without having a service interruption. If you have the whole network in a single routing domain, then that's not a problem. But
right.
If you have a geographically disparate network that you have OSPF and BGP and different protocols, that becomes an issue.
Yeah, I see your point. I'm not sure how we would be able to do that. In this example, the way we did it is that all the internal connectivity was actually coming in this OSPF link. So there's an internal network connectivity coming into this environment right here to the internal users coming into this environment. So we're controlling it using OSPF right here. This BGP was going across to the edge routers, and we have BGP here. I'm not sure why I put the OSPF link up there. So So that's why we had to bring all the way BGP down, have different VIPs to make sure we distribute the BGP VIPs, the external VIPs, right here on this MSFC into BGP and internally for OSPF, and we keep them separate. Internal users versus external users. I think I have the full configuration for this. If you like, we can go over that, because we had to go through a lot of testing to make this work. Any other questions? All right then. Thank you very much. In here.